Hello students, today let us discuss Unit 6, Chapter 7, Alternating Current. First of all, we discuss what is alternating current. Alternating current is the current whose magnitude changes with time and direction reverses periodically now. Now see actually what is happening here now. I can observe here in this case the current whose magnitude changes, magnitude is changing in the current now. Then another thing that when the magnitude is changing, let us find here another thing what is changing now, the direction also changes now. That means magnitude and the direction of current is changing. How it is changing now? Magnitude changes with time and direction of the current is reverses periodically here. Now this figure is there below. It is showing an alternating current. You can observe what happens now. This starts from origin 0 here and this goes up like this and again it comes down here. You can find in this case now what we are finding here, it was coming like this all the way, that you can observe here the direction is continuously changing. You can say this is it is positive and this happens to be negative. Again this becomes positive and this again becomes negative now. Likewise the direction is changing now and its magnitude also changing now. That becomes high, plus 5 and minus 5 like this, plus and minus like this. That means periodically it is changing its direction as well as its magnitude now. That is why this is called the alternating current and it was simply known as AC. AC is for an alternating current. Now one cycle of the AC now. Now you see in the figure it is one complete cycle of the AC. That means you can start from here, this starts from 0 and it makes one complete rotation up to say for example 2 pi here. 2 pi means 360 degrees and you can call this point as a pi now. This is one complete cycle is there. But this one complete cycle is divided into two parts now, that positive half cycle here and here it is called a negative half cycle. The upper half is called the positive half cycle from 0 to pi and pi to 2 pi is a negative half cycle. It is a lower type like this. AC completes one cycle of 360 degrees. 0 to pi is called the 180 degree and it is a positive half cycle and the below one is there, it is a negative half cycle. Now let us see what is a period now. The period is time required to complete one oscillation. Now we have marked there from here, from this point to this point is a period. Now this is one complete, this is say for example this is one complete cycle is there. The time required to complete this cycle is called again one period now. So similarly you come here from here to here, the time required to complete this one cycle is also called again period now. It is 20 milliseconds per division is shown here. The period is defined as time required to complete one oscillation. Now the frequency, another terminology is there. Okay, see there are two figures are there. Now here I can show the low frequency here and this is high frequency. The frequency is number of oscillations made in 1 second now. Low frequency you can say the same length is there, same time period is there, but oscillations are less here. But in the second case high frequency oscillations are more. Come other figure here, this is time is same for all the four figures I have shown here. First one is 500 Hertz in a low frequency. See the oscillations here, one half oscillations here. Then this is 8000 Hertz now, the number of oscillations increase here. 33,000 Hertz now, number of oscillations still increases there. 130,000 oscillations increase now. Now this tells about the frequency of AC. Frequency is number of oscillations made in 1 second now. The number of oscillations made in 1 second is more, then it is called high frequency, and number of oscillations made in 1 second is less now, it is called again low frequency. Now what is the relation between period and frequency now? The frequency and period are related by the relation, it is F is equal to 1 upon T. You can say this frequency now. The frequency is always equal to 1 upon time now. The periodic time is more, then frequency is less. Now here, this is time required to complete one oscillations from here to here, and you see, for example, time required to complete one oscillations from here to here is. This time is very less as compared to this time now. That means here what happens now, the frequency is more, time is less. The frequency is less, time is more now, and this expression gives the relation between period and frequency. Now phase is the time elapsed by either current or voltage from its initial point now. You can see here, you can start with this figure now. This is 0 and this is 180 degree, this becomes 360 degree now. This is phase 1 now. Phase 1 starts from 0 now. But phase 2 starts from here. You can see this is phase 2 starts here. And similarly phase 3 starts from here now. You can see all the three of different starting points are there. Now compare this phase 1 and phase 2. What you will find that the phase 2 starts after the time that after more than 90 degree now, it starts here, and phase 3 starts less than 90 degree now. There is a phase difference is there. That is why they are shown by phase 1, phase 2, phase 3. All the phases are there. You can find here the phase 1 and phase 2, there are difference 120 degree and 120 degree phase difference is there. Now this tells about the phase and time elapsed, that is from starting with the 0 degree. Now coming to the instantaneous value now. Instant is the moment of time. You see in this figure, in this graph, you can see I show this is a current I1, this is current I2, this is current I3 like this. Like this you become all the way here like this, and this becomes as current IM. Similar, this becomes time 1, this is time 2, time 3 like this, this becomes as a time N now. For different time intervals, there is different value of current is there. Now here I1, I2, I3 and IN are at instant of time, T1, T2, T3 are the times now. You can see that at that time you have different currents are there, and they are known as instantaneous value of the current. Now this is one of the most important derivation in LCR circuit. The statement of the question is derive expression for resultant voltage. You can see here the expression becomes like a resultant voltage now. I will show it like this. This is your resultant voltage here. This is impedance and current, and also you can know that the phase angle. The four factors we wanted to derive here, and this is the circuit we can take for reference now. It is LCR series circuit is there. L is the inductor, C is the capacitor, and R is the resistance here. Let us say this becomes an AC source here, and this AC source is having the voltage V is equal to V0 into sin omega t. The similarly voltage across VL is voltage across inductor is called as VL, that of capacitor is called as VC, and that of resistance is called as VR. And this is, we have called as a phasor diagram of this one is drawn here, and you can see this is called as a phasor diagram, because the question itself they are told that using phasor diagram, they are told like this phasor diagram. Now this phasor diagram you have shown, you see here, this you can call the values for this one will be like this. You can call some values for them. Let us see. Let us first take the values for them like this now. This we can call as a O, okay. Then we can call this as a, and this is called as a B, and this is called as C now. Okay, this is called as C here, and this is called as your angle is called as a phi. Now here what happens now? The OB becomes a hypotenuse, and this is the opposite side, this one, and this becomes an adjacent side. This is opposite side and adjacent side. This is right angle triangle. That means we can apply the Pythagoras theorem for this one, and let us go to the next slide to study the Pythagoras theorem of this one now. Now what this Pythagoras theorem is now? This is your right angle triangle. You can draw a right angle triangle for this one, and this happens to be a right angle triangle, and you know this is our phase angle phi. We have called this as A, this is called as a B now, and this is called as a C now, ABC. Now for this one we wanted to find the what is side, hypotenuse now, that means OB is equal to, you can apply the Pythagoras theorem for this one, that is a OB square is equal to, you can write BC square plus this becomes as OC square. And you have seen this figure also. This is named as one value, and this is named as one value, this is another value. What exactly this was now? That means this we have what is as a, this value is what is a V now. We have what is the figure V, and this was what as a VR, and here this value is called as VL minus this becomes as VC. This is VL minus VC is there. Let us substitute these values into the figure. What you will find now? OB square, this becomes as V square. OB is there, V square is there, which is a resultant voltage is there. Then BC square becomes, for example, this is VL minus this is VC whole square now, and OC square becomes this is VR square. That means we substitute the values here. From this, what happens now? This is you can call this as a V square equal to, you can write this equation once again. V square is equal to, this becomes voltage across resistance square plus this difference is VL minus VC whole square. And this equation is there. You can call this as equation number 1, which is giving you the voltage or resultant voltage across your LCS circuit that is to be calculated now. Now here we can substitute the values for this also. That means we can write VR is equal to V is equal to I into R. V is equal to I into R now. Then for VL we can write as I into this XL is capacitive reactance. That also VC is equal to, we can write I into this is XC now. X is an capacitive reactance, XL is inductive reactance, and R is resistance. We can substitute in equation number 1 now. Now this becomes as, here you can say VR, that means I square, this becomes as a R square, this is VR square now, V is equal to I into R. Then this plus, here you can say X, this is I into XL, sorry, I into this becomes as XL now, this becomes I into XC whole square. Now from this square you can take I square common here. Now this happens to be, you can write for example, the I square comes out from this one, this is I square equal to, you can write into bracket now, this is R square, and here, now this becomes, once you write R square now this plus into bracket XL minus XC whole square remains here. And this is as a square, in which this becomes as a V square. Now when V square is equal to all these values are substituted in this one now, then what happens here? You can see simply the I is common here, you can again modify this and you can write V is equal to I into R. This becomes as a I into V is equal to, this was I into R. That was V square is equal to I square R square. Now this is I square R square. Now this equal to, and whatever written it was I square here. This is into bracket, we wanted right here, this is R in plus, now this becomes as XL minus XC whole square. XL minus XC whole square. Now the I is common on both sides and you can write as a, therefore you can write R square is equal to, now this becomes as a R plus, and this is XL minus XC whole square. Now then you find the value of the R. Now this becomes as square root of, this is here. Now this was actually R square was there here. This also R square, right? This is R square plus, this happens to be XL, this is XC whole square. Now this is your resistance is there. The resistance can be obtained like this. That means the finding V is equal to I into R now. But this was AC resistance, we can call it as Z now. This becomes as Z is equal to square root of, this is R square, this is XL minus this is XC whole square. It is called as the impedance. Impedance is called as the AC resistance now, and you can write this is a Z is equal to like this. Z is equal to square root of R square XL minus XC square. And if you wanted to find I is equal to, for this one now this becomes I is equal to, this is V upon I is there. Now this is V upon I means you can divide this by I now, I gets cancels here. Sorry, this is Z is equal to V upon I is there. Then I is equal to, you can write V Ohm's law, and you can write V upon Z here. Now this you can make it as a Z of this one. That means V divided by, you can write under the square root of the value of the Z can return here, and this becomes as R square plus this is XL minus XC, this is whole square. Now this equation gives us the current. The current can be calculated from this one. This equation helps us to calculate the current of this one. Then if you wanted to find the phase angle, that means you wanted to find the phase angle of this one. Now the phase angle becomes equal to, this is a tan phi is equal to opposite side upon adjacent side. Now this becomes as a BC from that figure upon this is a OC now. Then if you substitute the values for this one, this becomes as here in the, it becomes as VL minus VC and whole divided by, you can write it as a VR. That means this is auto the phi. Now you can say that this phi is equal to, you can write tan inverse of VL minus VC divided by VR. The phase angle can be obtained from this one. The phase angle that I told you to find now, you can find the phase angle from this one in this fashion. This is our fourth requirement was there. We have calculated the first, what is voltage, then current now, then I calculated resistance which is impedance, and you also calculated the phase angle. This is a requirement of our question now. That means the first was a resultant voltage. This was a resultant voltage was there, and this is given by V is equal to I. This is your impedance was there, that becomes as R square. This becomes XL minus XC whole square. Now this is for V is equal to I into R. The second was impedance. This was given by Z is equal to square root of R square plus this is XL minus XC whole square. This is called as an impedance now. Then your current is there. The third one, that is I'll write 3, I is equal to voltage upon Z is there. This is written V divided by square root of this is R square plus XL minus XC whole square. The third one. And fourth was there. It was phi is equal to tan inverse of your return. And this becomes as VL minus VC upon this is R. This is the actual, the required answer for this question. This question answer is completed here, and this is a clear cut picture is there now that we have calculated all the 4 requirements of that one, and this happens to be the perfect answer for this one. Now let us discuss some special cases for this one now. It was there, say for example our question that was impedance Z is equal to this was R square and this plus where written it was XL minus XC, this was whole square. This was our question was there, that is for the impedance now. Yes, suppose you see it is case like this, XL is equal to XC is there, then all this becomes 0 now, therefore this is Z becomes equal to R. That means it is the LCR circuit is said to be pure resistive circuit it is. This is one thing now. Another thing was there, XL is greater than XC. In this case then what happens now? This becomes your tan phi is there now. Now this becomes, this is a positive in this case. That means there is a upper half cycle, and you say that when XL is less than XC is there, then your tan phi is there. This happens to be negative. This is lower half cycle. That means tan phi becomes negative. Then you can say this is called a resistive circuit. This is a inductive dominated circuit, and this is called a capacitive dominated circuit. Now, like this you can conclude the 3 cases upon this one, and these 3 cases helps us to finalize the content of the circuit by using the above formula, and that above formula tells us that what exactly the circuit was there. You can say this circuit was a LCR circuit. In this one you have done, that is the impedance value Z here. The second was there, the impedance you have calculated now. Then you have calculated what is a voltage also. Third you have calculated what is a current also. And fourth you calculated what is a phi values also. And also you studied from this one, Z is equal to this was square root of R square plus this is XL minus XC whole square was there. And this is you are discussed with, for example, first case was XL is equal to XC, second was XL is greater than XC, and the third is there, XL is less than XC now. Now this was called the inductive dominating circuit, and this was a capacitive dominating circuit, and this is called a resistive circuit now. Like this you can conclude the answer and the further discussion about this question now. And dear students, I hope I have tried my level best to convince you this part of the syllabus, and thank you one and all for joining this one. I hope the best of luck for you people, and let us continue. Okay, let us continue this for further classes now. Thank you one and all.